Let's do another example now, which will both act as a review for finding electric potential and set the stage for finding electric potential due to continuous charge distributions. So let's say we have 7 charges, and each one has charge 1.25 nanocoulombs. I'm going to call that Q. So every single charge has this charge. And every charge is separated by 1 millimeter. Let's see if I can squeeze that in the diagram. So 1 millimeter, 1 millimeter, and so on for all of them. Okay, so they're all evenly spaced out. Find the net electric potential at point P, which is a half a millimeter from charge Q4. So let's put point P on our diagram. That's going to be right here. And the distance from here is going to be x equals 0.5 millimeters. Okay, I'm sacrificing significant digits for space here. So net electric potential, we remember that we find potential V equals K times Q over R. Electric potential, like electric potential energy, is a scalar. It doesn't have a direction. So if this were an electric field problem, we would be drawing all of the electric fields, and we did that before. This is a scalar, so we can't draw any arrows because it's not a vector. So to find one electric potential, we do KQ over R. R is your distance between your charge and your point. To find a bunch of electric potentials, or let's rephrase that, to find the total electric potential due to a bunch of charges, we'll find our total potential is the sum of each individual potential, which is the sum of K times each charge divided by each distance between that charge and the point we're trying to find the potential. Okay, here we have 7 charges, so we're going to have to find 7 potentials. So my potential due to charge 1, maybe I'll grab a different color for each charge if I can do it. So I'll use red for my first one. So my first charge, Q1, oops, my alarm just went off. There, turned off. So my potential due to my first charge is V1. It's K times Q1 divided by R1. Q1, I'm just going to call Q, and R1 is my distance between my charge 1 and my point P. So there is R1. I've got to figure out R1 from my geometry. So R1 is the hypotenuse of a right angled triangle. The legs are 0.5 millimeters and 3 millimeters. Okay, so maybe I'll even try and put that in the diagram over here. So 0.5 millimeters and 3 millimeters. So KQ1 over R1. R1 is the square root of 0.5 millimeters squared plus 3 millimeters squared. So the value of R1 is I'm going to keep a few extra sig figs here, 3.0414 millimeters. Okay, I'm going to put this in my expression for potential. K 8.99 times 10 to the 9 times 1.25 times 10 to the minus 9 divided by 3.0414 times 10 to the minus 3 to get a total potential V1 of 3,695 volts. Okay, that's V1. What about V2? So I'll use blue for my R2. So V2 is equal to K times Q2 divided by R2 equals K times Q divided by R2. So Q1, Q2, they all have the same magnitude. R2 is my distance between charge 2 and my point. R2 is a hypotenuse of a right angled triangle where the legs are 0.5 and 2. So my R2 is the square root of 0.5 millimeters squared plus 2 millimeters squared. This charge is a little bit closer, so we're thinking the potential is going to be a bit bigger. My R value is 2.0616 millimeters, and that gives me a potential 8.99 times 10 to the 9 times 1.25 times 10 to the minus 9 divided by 2.0616 times 10 to the minus 3 gives me a potential of 5,451 volts. Okay, let's do 3 next. So my potential V3 is K times Q3 over R3. Q3 has the same magnitude of charge as the rest of them. R3 is my distance between charge 3 and my point. Draw that on the diagram. R3 is the square root of 0.5 millimeters squared plus 1 millimeter squared. So my R3 is equal to 1.1180 millimeters. Put this in my expression for my potential, and I get a bigger potential still because I'm even closer, 10,051 volts. Okay, let's do 4 next. So my Q4 has a potential associated with it, V4, K times Q4 over R4. R4 is the distance between my charge and my point. So R4 is just equal to X equals 0.5 millimeters. So now that I'm getting even closer, I expect my potential's getting even bigger. 8.99 times 10 to the 9 times 1.25 times 10 to the minus 9 divided by 0.5 times 10 to the minus 3 meters gives us a potential due to R4 of 22,475 volts. Okay, next we got lots of symmetry going on down here. So let's go to charge 5 next. So charge 5 has a distance of R5 from my point. R5 is the same length as R3. It's the square root of 0.5 squared plus 1 millimeter squared. So R5 equals R3. That means V5 equals V3 equals 10,051 volts. Okay, what about 6? So charge 6 has the same distance as charge 2. This is R6. So R6 is 0.5 squared plus 2 squared. That's the same as R2. So R6 equals R2. Same distance, same charge, same potential. So V6 equals V2. Remember, when this was an electric field problem, we had Y components canceling, X components adding up. Potential is a scalar. We don't have any components to find, so the components can't be canceling. We're just going to be adding up the numbers. Really important to keep in mind what's a vector and what's a scalar. So my V6 is the same as V2, 5,451 volts. Last charge is charge number 7. My distance for 7 is the same as my distance for 1, so R7 equals R1, same distance, same charge, same potential. So that potential is 3,695 volts. To get my total potential now, I'm just going to add up all 7 of them. So my net potential V total is V1 plus V2 plus V3 plus V4 plus V5 plus V6 plus V7. So that's going to be 3695 plus 5451 plus 10,051 plus 22,475 plus 1051 plus 5451 plus 3695 gives us a total electric potential of those 7 charges equal to 60,869 volts, and we might prefer to write that with 3 sig figs, 6.09 times 10 to the 4 volts. So there's the net electric potential due to this system of 7 charges at point P, which is just across from charge Q4.